Hello and welcome to Paracetamol Academy. My name is Marc Enlian, currently a fourth-year pharmacy student at the Lebanese American University. You are watching Chapter 2, in which we will tackle physicochemical properties of a drug and the factors affecting access of the drug to the site of action. It might sound intimidating, but do not worry, because we are here to walk you through all of it. I want this video to introduce you to the vocabulary you will come to be familiar with during your professional pharmacy studies. The approach will combine, therefore, the coverage of notions of medicinal chemistry to a quick overview of what is to come in terms of pharmacokinetics, implications in clinical practice, and in dosage forms formulation, as well as practice on the notions wherever applicable. In medicinal chemistry, the focus is on the physicochemical properties of various drug categories, their relation to biological activity, metabolic pathways, structure-activity relationship of the drug, and their adverse effects as well. You will be learning in later videos about drugs affecting the adrenergic nervous system and the cholinergic nervous system, which you may know as sympathetic and parasympathetic divisions of the nervous system respectively, as well as analgesics, which are painkillers, anesthetics, antidepressants, antihypertensives, and much more categories to come. The first part of this presentation will cover, in a nutshell, necessary general notions. What are the physicochemical properties of a drug? How are drugs classified? And how a drug produces its biological activity. The physicochemical properties of a drug really are all the properties that invoke the pharmacological response on the receptor on which the drug will be acting. In simpler terms, this means that these properties pretty much determine how, what, where, and why the drug acts the way it does inside our body. Physical properties include the following list, which you should be familiar with, and on which point I will be explaining a little bit. But they are not limited to the following: solubility of the drug, whether we are talking in water or other solvents; acidity and basicity, which are determinants of solubility and of eventually the concentration of a drug that will be absorbed into our body; the partition coefficient, which is the ratio of concentrations of a compound in a mixture of two immiscible phases at equilibrium, such as, for example, the partition coefficient of a drug in, let's say, water to octanol, water being very aqueous and octanol being very high in lipid content, so a very fatty liquid. Also, the degree of ionization of a drug, which is, let's say, a function of acidity and basicity really, the presence of intermolecular forces, and surface activity of a drug, which is the ability of the substance to alter the nature of a surface or an interface between two substances. Eventually, hydrophilicity and lipophilicity of a drug are also determined by these properties. And the following terms really mean that a drug would prefer to be an aqueous medium if it is hydrophilic, or it would prefer a fatty medium if it is lipophilic. And both of those have their implications in practice and in the way that the drug behaves depending on which site it is present at in the body. The chemical structure and the stereochemistry of a drug represent their chemical properties as determinants of affinity to a given receptor. Drugs can be classified with regards to various approaches. For example, when it comes down to the origin or the source of the drug, it could be natural, it could even be herbal, which is the field of pharmacognosy. It could be semi-synthetic or fully synthetic, as opposed to being of natural origin. Or it could be biosynthetic, which is the trend of the future. And this is where you hear about biosimilars and drugs that are adapted for personalized therapy. The drug can also be classified according to its therapeutic use. So, for example, whether it is an anti-diabetic drug, an anti-anginal drug, an anti-cancer drug, an anti-hypertensive drug, and among those therapeutic uses, a drug can be massively different in terms of chemical structure or even in terms of physicochemical properties, but still respond within the same therapeutic use. Or we can classify the drug according to the site of drug action. So for example, drugs that are called beta blockers will be blocking the beta receptors that are in the body. Similarly, we have drugs called ACE inhibitors, we have drugs called alpha blockers. So the site of drug action can also be a marker of classification. The pharmacological action of the drug is pretty much what the drug does, and the way it differs in the therapeutic use is that the pharmacological action is what leads to the therapeutic use. So for example, we say vasodilation, and vasodilation can lead to a given therapeutic use, or bronchodilation, or diuresis. So for example, a drug that produces diuresis can eventually be used for antihypertensive effect, which is the therapeutic use. And finally, we do classify drugs according to their chemical structure as well. For example, antibiotics of the family of beta-lactams are antibiotics that feature a lactam in beta position. We also have barbiturates, we also have steroids, penicillins, which are another category of antibiotic. So the chemical structure can also be how we classify drugs depending on the drug itself. When we bring up structural specificity into play, it refers to whether the drug's activity is predominantly owing to its physical or its chemical properties. A structurally specific drug means that the action results from its chemical structure's specificity. Let's look at this example. Epinephrine and isoproterenol. With the addition of only two methyl groups to form an isopropyl for isoproterenol, as it is marked in blue on the drawing, as opposed to epinephrine's singular CH3 methyl group on the free end of the secondary amine, the therapeutic use of the drug was completely reversed from producing hypertension for epinephrine to being an antihypertensive that produces hypotension for isoproterenol. In stark contrast, we can talk about structurally non-specific drugs, which refers to drugs whose structure is not a major driving for the biological activity. Instead, those drugs count on their physical properties instead to produce their action. The following drugs in this scheme are all volatile anesthetics in gaseous form. Despite sharing nothing in common structure-wise, such as cyclopropane compared to the massively different methoxyflurane, all of these drugs produce anesthesia. These drugs' physical properties would also go on to determine whether the drug has a rapid induction or a slow induction, which is the time for onset of action, as well as the recovery speed, which is proportional to the time of induction. Let's do a logical walkthrough. An anesthetic's action depends on how fast it reaches the brain, right? For this to occur, the drug has to reach the bloodstream. Would you expect a drug that is highly soluble in blood to reach the brain faster? Focus, I will repeat the question. Would you expect a drug that is highly soluble in blood to reach the brain faster? Pause and think about it. 4, 3, 2, 1. And the answer is more blood soluble means more time for saturation in the blood, so a longer time to saturate the blood and reach, leading to a slower onset of action and a longer recovery time, because then the drug would have to spend more time saturating the blood and therefore takes longer to reach the brain, logically. The opposite is also true, and so among the drugs presented here, nitrous oxide is completely inorganic and is therefore the fastest acting but shortest acting anesthetic too in this list because it is very insoluble in blood compared to, for example, methoxyflurane, which has a high partition coefficient of blood to gas and therefore a slower induction time but also a slower recovery speed and a longer effect overall. We are gonna do another application on the physicochemical properties. This time it's written on the slide. Let's look at the table here. If we look at the compounds in this table, we can see that the first one, called thymol, has a very low bactericidal concentration of 0.0022 molars, required to be lethal to bacteria. This is such a low concentration. At the same time, the solubility of thymol in water is pretty much null. It has a very low solubility in water. In contrast, methanol is almost infinitely soluble in water and completely miscible to it, and it requires a concentration of almost 10 molar, even 11 molar of concentration to kill bacteria. This table shows us how the physical property of solubility determines the drug's bactericidal action, in that the more polar the compound is, meaning the more soluble it is in water, the higher the concentration required to become bactericidal. In your opinion, does that mean that the drug would be called more potent or less potent if it requires a higher concentration to work? Pause and think about it. 4, 3, 2, 1. And the answer is, the lower concentration required for a drug to give us its effect, the more potent it is. This is logical. If you need less concentration of a given drug so that it does produce its therapeutic effect and its pharmacological action, then the drug can be called stronger, more potent, requiring a lower concentration to give us its effect. Finally, how does a drug produce its biological activity? In a nutshell, most drugs will bind to a receptor at the surface of the cells of the targeted organ, producing a complex of a drug receptor, leading to a biological response. We also say that the drug elicits a biological response. This binding depends on the aforementioned physicochemical properties of the drug, which will determine how much affinity the drug will have to the receptor. Another consideration to keep in mind is the stereochemistry, which we did mention a couple of slides ago. In this example, for example, we have two stereoisomers of epinephrine, plus which we will call dextro, and minus which we will call levo. Now, levoepinephrine can bind the receptor on two A sites, a B site, and a C site, according to the scheme on the left, whereas dextroepinephrine can only bind 3 of those 4 sites. As you can see, the stereochemistry of dextroepinephrine does not allow it to form a hydrogen bond with the B site of the receptor, meaning that one of the receptor is not binding. And for this reason, levoepinephrine has a higher affinity to the receptor because it has more sites to bind it. And therefore, the levo enantiomer of epinephrine is more active than the dextro. Moving on to part 2 of this presentation, here are factors affecting the drug's access to the site of action. These are notions of pharmacokinetics at this level. In fact, this is the definition of pharmacokinetics in a nutshell. The factors affecting the drug's access to the site of action, by which it can therefore produce its effect, are its absorption, its distribution, its metabolism, and its excretion. For people who like graphics, here's a nice graphic. In a nutshell, absorption deals with how the drug gets in, distribution with where the drug goes and by what means it goes there, metabolism, how the drug is broken down in the body, and excretion, how the drug leaves the body. We can sometimes group metabolism and excretion under a bigger umbrella term of elimination because metabolism will eliminate the original molecule. Now, metabolism will be covered as a standalone chapter, so we will approach quick notions of the remaining steps of this ADME scheme that is the base of pharmacokinetics, and which is determined by the physicochemical properties of the drug again and again. A quick word on the route of administration of a drug. This one will be interesting for people who like practical matters. Now, the route of administration of a drug can have a massive influence on the bioavailability of the drug. Bioavailability refers to how much of the drug is available in the blood to produce its action. As metabolism will cover, many drugs are extensively modified by the liver, the major organ carrying out metabolism, and therefore losses of the original drug occur at the level of the liver before reaching the organ that it wants to target, depending on the route taken. However, losses of the original molecule is not always a bad thing, because some molecules are formulated as what we call a prodrug, meaning that it is completely inactive in the way that it is taken, and once it is metabolized inside the liver, it is going to give us an active compound, which is going to act as a drug. this is a very innovative way of formulating drugs. But in most cases, metabolism tends to inactivate the drug. Now, if we look at the scheme, do you think that oral administration or intravenous injection would result in a higher availability of the drug in systemic circulation? Pause and think about it. 4, 3, 2, 1. And the answer is a more invasive route, such as the intravenous and even intra-arterial route, results in much better bioavailability, because an intravenous injection completely avoids the liver, which is the major organ of metabolism. So a drug that is not formulated as a prodrug for IV injection is going to reach the bloodstream almost instantly, leading to nearly no loss related to metabolism. However, such a route is considered to be invasive. And at the level of industry and dosage forms, these are much harder to produce due to the precision and the sterility requirements. And some drugs can simply not be formulated at the low volumes required for IV injection. Overall, the oral route remains the more popular one for administration both among the population and the industry. It is much more convenient. We can swallow a pill much more easily than receiving an IV injection. It is much less challenging to formulate, and it is suitable for most active pharmaceutical ingredients in the world. Forgive this small excursion to dosage forms materials. And we are back to absorption of a drug. It occurs via passive diffusion for non-ionized forms and active transport for ionized forms. Now, most ionizable drugs are water-soluble because they can form H bonds with H2O molecules, but this is not always the case. I'm going to show you an example in the next slide. As you can look at tyrosine, it is in Zwitter ionic form here, meaning that it is at the pH where both of its groups have been ionized. We can look at the pKa NH2 of pKa 9.1 and the carboxylic group, which is also ionized. As we can see, because NH2 carries a positive charge when ionized, becoming NH3+, and the carboxylic acid giving us a negatively charged group, COO-, those opposite charges will have the tendency to attract each other, and therefore the drug will form intermolecular forces, rather than forming a hydrogen bond with the H2O molecule, giving us an ionized compound that is, however, very, very poorly soluble in water, because its groups are busier interacting with each other than interacting with water. This takes us back to the fact that if a drug has more than one ionizable functional group and they produce opposite charges, they may bind each other instead of binding the water molecules, resulting in a polar but hydrophobic compound. Now, for drug and pH, we have each of the functional groups present in the chemical structure of the drug having its own pKa, a number which, when it is equal to the pH, results in 50% of the drug being ionized and 50% being non-ionized. As a general rule of thumb, ionized drugs are more hydrophilic and non-ionized drugs more lipophilic, and lipophilic drugs are better absorbed by cell membranes for the most part and can cross the blood-brain barrier as well to reach the brain, a notion that you will commonly see in the upcoming chapters, and all concepts that will be covered extensively in the coming chapters. Now let's talk about acid-base coefficient. The simplest way to memorize this is that most drugs are either weak acids or weak bases, and weak acids will tend to be non-ionized in their environment, leading to an optimal absorption in an environment that is in their image. A weak acid is better absorbed in the stomach, which is acidic. On the other term, the weak acid is going to be ionized in the opposite environment in which it is. So a basic environment is not suitable for the absorption of the weak acid. So a weakly acid drug is poorly absorbed in the intestine. For weak bases, it is the complete opposite deal. They have optimal absorption in the intestine and minimal absorption in the stomach for the same reason. Weak bases prefer basic environments such as the intestine compared to the stomach, which is extremely acidic and even extremely harsh to many drugs. We sometimes talk about enteric-coated drugs. These drugs are coated in a way that the stomach cannot degrade them, and then the coating in which they come in, as in the pill having the coating, will eventually dissolve in the intestine only. And this is also an innovation in dosage form that makes use of the physicochemical property of the drug to determine as a factor where it is going to be absorbed. The equation of Henderson-Hasselbalch can be used to calculate the percentage of ionization of a drug. We interpret it with regards to the specific given pH, and this is extremely important. The acid-base coefficient, we're going to have an application of ibuprofen. Let's look at ibuprofen and its pKa of 4.5. What is the ratio of ionized to non-ionized ibuprofen in the stomach at a pH of 2.5 and in the small intestine at a pH of 6.5? In the stomach at a pH of 2.5, we're going to calculate looking at this nice equation, which you will learn to apply. pH equal pKa plus log of base form over acidic form. Doing all calculations, this gives us of log of B over A equal to 2.5 minus 4.5. So log of B over A is going to be equal to minus 2. The way you get rid of the logarithmic function in mathematics is that you pretty much give it as 10 exponent of. So for log B over A being equal to minus 2, B over A is going to be equal to 10 exponent minus 2, meaning 1 in 100. So the ratio of base, ionized form, to acidic, which is non-ionized form of ibuprofen in the stomach, is 1 to 100 at a pH of 2.5. Ibuprofen will therefore be more absorbed in the stomach. In the small intestine at a pH of 6.5, the calculation gives us a ratio of 100 over 1. So the ratio of base, which is the ionized form, to acidic, the non-ionized form of ibuprofen, is 100 to 1 at a pH of 6.5. Ibuprofen will be available in much more ionized form, so it will be less absorbed in the small intestine because the ionized form has a poorer absorption compared to the non-ionized form. Another application for amphetamine this time. If we look at the calculation, in the stomach, the ratio is 1 in 10 million, and in the small intestine, it's 1 in 100. For implications, this means that the stomach, amphetamine will be mainly in its acid, ionized, very polar form, so it's going to be a very difficult drug to absorb, 1 in 10 million. Similarly, in the small intestine, the major form remains the acidic form, and so amphetamine is still not very easily absorbed in the small intestine. Some drugs are simply more challenging when it comes down to their absorption, and this is determined by their physicochemical properties again and again. In terms of distribution to various tissues will be depending on the physicochemical properties of the drugs, as you have guessed it. Drug distribution to the CNS, the central nervous system, depends on the pKa of the drug as well as its lipophilicity. Distribution of a drug between blood and fat is also related to the fat-to-water partition coefficient. And drugs with a high fat-to-water partition coefficient will tend to accumulate in adipose tissue. Now, most drugs undergo what is called protein binding in the plasma. They bind in a reversible fashion with plasma proteins such as albumin for their transport. So a drug plus albumin is going to form a drug and albumin complex. The effects of protein binding is that protein binding will prevent rapid renal excretion because the complex becomes therefore too large to pass by glomerular filtration, which is one of the mechanisms of elimination. It's also going to limit the amount of drug available for metabolism and interaction with the receptor site, because only unbound portion of the drug can cross biological membranes and only free drug molecules will account for their activity. This is a graphic for those who prefer graphics. Eventually, we're going to have decreased plasma protein binding leading to increase in free plasma fraction of the drug. So the lower plasma protein binding is, it's going to cause an increase in volume of distribution and a shorter elimination half-life, which are all concepts extensively covered in chapters of pharmacokinetics. Now, in terms of protein binding and what it implies in practice, we always have concerns with drug-drug interaction. This is prevalent in people on polypharmacy. Polypharmacy meaning a person is taking more than one drug. And this is very prevalent among the older population and older adults. Because drugs rely on body's receptors and proteins for absorption, distribution, and elimination, drug-drug interactions can very often happen at this level. An example, phenylbutazone, which is an anti-inflammatory, competes with warfarin, an anticoagulant, with the same binding site on albumin. They're going to compete for the same site, which means that the presence of phenylbutazone will reduce available warfarin. Implications in practice. Warfarin is an anticoagulant with a very narrow therapeutic index, meaning that any fluctuation in its available concentration can have a severe impact on its anticoagulation effect. And if it cannot produce enough anticoagulation, then it's going to allow hemorrhage. And so hemorrhage might not be prevented properly in practices where phenylbutazone is taken with warfarin. So if this is absolutely necessary, the dose of warfarin should be adjusted in a way that the practice will account for the fact that warfarin is a narrow therapeutic index drug. And again, all of this is tied to the physicochemical properties of the drugs. This is pharmacology, this is medicinal chemistry, this is pharmacokinetics, this is everything you will come to learn throughout your pharmacy education. Couple of words on elimination. It may depend on glomerular filtration, which we did bring up. It takes care of compounds that are smaller in size, and we have mechanisms such as tubular secretion and tubular reabsorption. For tubular secretion, it is the elimination in an active fashion of ionized drugs, making use of specific transporters for organic acids and organic bases. An example of tubular secreted drugs include penicillins, and they can be given with drugs that inhibit tubular secretion in order to increase their availability. Because if you inhibit the specific transporters that eliminate the drug, you allow a drug to concentrate in a higher volume in the body. Tubular reabsorption is the passive transport which is affected by the drug's physicochemical properties, and it is mostly the domain of non-ionized drugs. The physicochemical properties at play for tubular reabsorption are the lipid-water partition coefficient and the ionization degree of the drug in urine. And this is a graphic that shows what is happening. So in a nutshell, at the proximal tube, we're going to have the availability of passive reabsorption, so tubular reabsorption, but also we have active secretion with those organic acid and organic base transporters as they are present. In the distal tube, we have much more the presence of those active secretion components. So this was, for us, chapter 2, in which we did tackle the physicochemical properties of the drugs and the factors affecting the access of the drug to the site of action. The presentation was loaded in technical terms, and again, this should be serving you to be well acquainted with the vocabulary that will come to be everywhere in your studies, in every course that you will be taking in your professional pharmacy education. Thank you for watching. This was Paracetamol Academy. If you enjoyed this content, consider leaving a like and subscribing to our channel. We would really appreciate the support. So show us your support. Thanks for watching.